Greetings to you, dear learners. I welcome you once again to this channel and to another lecture video. In the past, we've been considering rotational motion, and we considered several quantities used in describing such motion. Along the line, we came across the concept of moment of inertia. Today, we are delving more into that concept, moment of inertia. Now, what is moment of inertia? Particularly relating to a rigid body. Moment of inertia is the measure of the rotational inertia of a rigid body. Measure of the rotational inertia of a rigid body. That is the reluctance of the rigid body to rotate about an axis. Also can be said to be the opposition to change of position by a rotating body. It determines the response of a body to rotational forces, and it is a scalar quantity. The unit is in kilogram meter squared. And moment of inertia depends on the following. One, the mass of a body. Depends on the mass of a body. We have 2, 3, 4 bodies with different masses, then their moment of inertia will differ. It will be of the same shape, but as long as they have different masses, the moment of inertia will be different. And I use that as an example. You have a body mass. The body mass M1 and the body mass M2. As long as the masses are not the same, then the moment of inertia of the two bodies will not be the same. Also, it depends on the distribution of the mass across the body. Recall, we consider center of mass, that is the position of different masses, particles that makes up a system, different particles that make up a system. So even when we have a body, or two bodies rather, of the same mass, the absolute mass is the same. However, the mass are concentrated at different positions within the body, then it will affect the amount of inertia and cause differences in the moment of inertia of these two bodies. And this gives us an illustration. Though they have the same mass, m, we will see for the mass on the left hand side, the mass is distributed more towards the center, so that it's concentrated more towards the center. I use the darker part to represent higher concentration of masses, and the lighter one to the lower one. So for the mass on the left hand side, the mass is concentrated towards the center, and for the one on the right hand side, the mass is concentrated towards the edge. This will also lead to the difference in the moment of inertia. Though they are the same shape, though they are the same mass, but because of this, their moment of inertia will be different. Also, the axis of rotation of the body. That is, if you have a body, the moment of inertia of that body is not constant, because the axis, the configuration of the rotation, of the axis of rotation, will also affect the moment of inertia. And look at this figure again as illustration. You see, on the left hand side, the axis is through the center of the cylinder or the disc. through the center. But here, it is not through the center. So though they have the same mass, and the distribution of masses is the same, the distribution of the masses is the same, but the differences in their axis of rotation will also lead to differences in their moment of inertia. Generally, moment of inertia of a body, therefore, is given as I equals to mk squared. So m is the mass, which I told you they affect the inertia, body of different masses, they have different inertia. And k is the radius of gyration. And if you have the same mass and k is different also, then I will be different. Okay, so if you have two, three different bodies with the same masses, but their radius of gyration is different, then the I will be different. And again, that radius of gyration, K, is affected by all those things that we considered earlier. We still see again, for emphasis. The radius of gyration is the distance from the center of rotation of the rotating body to the point where the mass can be considered to be constricted. Do you get that? So, center of axis of rotation and the point where the mass can be said to be concentrated. For example, look at this. If I have a disk, let me look at it. If I have a disk, this is a disk. This is an example. This. Then I have this. Rotating. This is R, the radius of the disk. That is R. But let's assume that the disk, the more of the masses is concentrated more around here, across the something here. Then what happens is that the K will be a function of that distance. Okay, so if the mass is concentrated at this point, midway between the center and the edge of the disk, then the radius of gyration will be a measure of the distance between that point where the mass is considered concentrated and the center of the disk, which is the where the axis of rotation lies. Okay, so radius of gyration depends on the following: the size of the body. So we can have again different, the same shape, but the radius will be different. The length, if it's like a rod, different. Area, a two-dimensional object, different. Volume, a three-dimensional object. So the size will affect the gyration. Okay, but all the dimensions are different. Also, the shape of the body. That is, I may have two bodies weighing the same thing at the same mass, but one can be a rectangle, the other one can be, or one can be a cuboid, the other one can be a disc, then, or a sphere. Though they have the same mass, but their shape will cause a difference in their radius of gyration. Also, the distribution of mass in the body with respect to the axis of rotation. And I think the earlier translation also gives us that idea. Okay? Then, now that's it. They have the same mass, but the distribution of mass with respect to the axis of rotation. Look at it here. The distribution of mass is towards for the left hand side is around the axis of rotation, and the right hand side is towards the edge of the disk, away from the axis of rotation. So that means K will be higher for the one on the right hand side than on the one on the left hand side. Okay, according to the attribution of radius of gyration. Then the position and the configuration of axis of rotation will also affect radius of gyration. I think we explained that earlier. So give some emphasis on that. And you can see that I have a rod, but the same length. Look at it. From the far left, the center image, and one at the right, they have the same length. But the axis of rotation here, this one is rotating, and the axis is at the edge, and the rod is like flipping. That's rotation, flipping. At the center, the axis of rotation is at the center of the disc, of the rod rather, and it's also like flipping, like turning. But at the right hand side, the rotation is through the rod and it's rolling. Look at it, not flipping here, but rolling. So that position and configuration will also affect the radius of gyration and directly affecting also the moment of inertia. So the moment of inertia will be different in each presented cases. And we could see this table giving us an idea of the estimation of moment of inertia for common solids and the equivalent radius of gyration K. If I look at, as explained previously, you see for a uniform rod at one end, you see it like flipping, you see I to be ml squared over 3 and K is equal to L over square root of 3. Remember that I, moment of inertia, generally is mk squared. So if, for example, you have for the first one, your k squared is L squared over 3. So k, now square root of k will give you L over square root of 3. Okay, for the second one, the same rod, but at the middle. You see the difference? At the middle now, the inertia will be half of the radius of gyration will be half of if it's at the rod. That's why it is L over 2 square root of 3. Okay? The gyration will be half of the gyration when it's at the end. So again, see that the position of the axis of rotation, the configuration, affects the radius of gyration, which also directly affects the moment of inertia. Look at the disk. That's the third one. Circular disk about the center. So if the axis of rotation is through the center of the disk, look at this. Rotating disk. Then I is equal to m r squared over 2, and k is r over square root of 2. For the solid cylinder, about the axis of symmetry, look at the right side of the screen. You see it? That's the cylinder, a solid cylinder, no hollow, no space within the cylinder. In that case, moment of inertia I is equal to mr squared over 2, just like we have for the disk. And r, you see it, the radius of gyration is also the same. But when you have a cylinder that has space, a hollow cylinder, and it's also through this axis of symmetry, through the center, then you see, in this case now that I is mr squared and k is equal to r. Do you know why? You will now understand why. This is so because the left hand side, I'm trying to make your left hand side here. This is so because it has an hollow cylinder, so the distribution of the mass is towards the end of the cylinder, but there is no space in the core of the cylinder, towards the edge of the cylinder. Do you get it? So K will be approximately equal to R. The thinner, then the more closer the value of R to K. Look at that explanation. So it's very straightforward. Then for a solid cylinder or disc, we consider disc or cylinder before. For a solid cylinder or disc now, and the axis of rotation is not about the center, but about the diameter. Do you get it? It's about the central diameter. Look at where the rotation is now. So it's like flipping. The disc is flipping, not rolling. The cylinder is not rolling, but flipping. You get it? Then you could see that it's also the same. When it is rolling, both the solid cylinder and the circular disc rolling, the K is the same. Likewise, I. And for the solid cylinder and the disc, when the axis of rotation is about the center diameter, when it's flipping, you see that also K is the same and also I is the same. Okay? We have additional ones. For a solid sphere about any diameter, you have a solid sphere. A sphere where there is nothing, nothing inside the cylinder. A solid sphere, like a perfect spherical stone. That's solid. No hollow space, no space inside it. Then you have I equals to 2 over 5 mr squared. And the K is square root of 2 over 5 r. Then for and the hemisphere about analysis. Hemisphere about analysis. You have 2 over 5 mr squared. Okay, same thing. Now, but if the hemisphere is about any other axis, the first one is if the hemisphere is about axis of symmetry, that is passing through, cutting the hemisphere into almost 2 equal halves, then we'll see it, the K is equal to square root of 2 over 5 r. But if the axis of rotation is at other position other than that center, then you have another value of K, which is 0.509 r. For a thin spherical shell, okay, now this is shell where, or let me say, a shell is like a sphere, but it's not solid. There is hollow, there is space in it. In that case now, I will be 2 over 3 mr squared, and your K is square root of 2 over 3 half. Okay. Then for cone, I is 3 over 10 mr squared, and K is square root of 3 over 10 r. Then for that's the cone about the axis of symmetry. The axis of symmetry is like it's dividing the cone into 2 equal halves. But at other axis of symmetry, or also of rotation, axis of rotation besides the axis of symmetry, then we have I to be equal to 3m over 80, then multiply by open bracket 4r squared plus l squared bracket. In this case now, the length of the cone will be factored in. The length of the cone will be factored in. Okay. Then for a regular plate, so this is like anything cuboid or a rectangular plate, then I will be m over 12 open bracket l squared plus b squared close bracket. L is the length of the rectangular plate and b is the breadth of the rectangular plate, and from there K can also be obtained. So these formulas can be used to estimate the moment of inertia, any type of object, as long as the mass is known, the radius is known, and the length or breadth where that is applicable. Now, rigid bodies. These bodies are systems of particles wherein the distances between the system particles remain unchanged. So in the rigid body, distances between each of the particles that makes up that system is fixed. They don't change. Therefore, they suffer, and that's one of the characteristics of rigid bodies. They suffer negligible deformation when subjected to external forces. They do not deform. For example, your bicycle frame, you sit on it, it will not deform. Okay? Your coin, it will not. You stand on it, you sit on it, it will not deform. Even if you eat it with hammer, may not deform. It may not deform, depending on the, okay? Then they undergo motion that could be translational and rotational. Okay? For example, the coin. You roll the coin. The coin is rolling, and it is also going away from you. It's rolling, rotational, and it's away from you. It is translational. Then the mass within the system are distributed across the entire volume. So the mass is distributed across the volume, although it may be uniformly distributed, and it may not be, but they are distributed across the entire volume. And rigid bodies have moments of inertia, which is a function of their mass distribution and shape. I think we have emphasized that over and over. So for rigid body, for example, natural rigid bodies are made of different number of particles, n number of particles, and each particle has their masses. And we tag the mass of each particle m1, m2, m3, m sub n, and these particles are the distance of, or different distances, r1, r2, r3, r4, as it may be, from the axis of rotation. Then we can obtain their angular momentum. Okay, let's assume we have a system together. If you consider our previous example, you have two systems, you have three systems, the particles or bodies making up a system, then you can estimate the angular momentum using this formula. Because they are fixed, they will all have the same, as they rotate, they will all have the same angular velocity, omega. However, their mass is unchanging, and at different position may vary. Then the distance of this mass from the axis of rotation is also fixed. Remember, it's a rigid body, so you have m1 r1 squared, m2 r2 squared, m3 r3 squared, and so on and so forth. And you factorize the common term there, and you have the expression. So this expression is the same thing as what I have here, and that's our R. Okay. Now, look at this example. The mass of a uniform circular disc is 1000 grams, and its radius is 100 centimeters. We have the mass of a circular disc, mass, and you have the radius. Now, calculate its moment of inertia about an axis through its center. Now, it's about it's through the center. That means the disc, the axis of rotation is through the center. Do you get it? It's through the center. So calculate the moment of inertia. That's the first thing to do. Then the second thing is to calculate the energy stored in the disc when it makes 60 revolutions per minute. Okay? So the energy stored when it makes 60 revolutions per minute. 60 revolutions per minute, that means you are giving the angular velocity. Anything per minute, per second, it means we are talking of velocity. A revolution means angular, rotating, rotation. Do you get it now? So you know that already. So that's illustrates that. You have the plane of the disc, the axis of rotation. We know the formula for a uniform circular disc. For a uniform circular disc, we know the formula before. From that formula, we apply, we substitute our values between it. Note again, this value is in grams, and we have to work with SI units. So we convert to kilogram, and also R in centimeters, convert to SI unit to meters. Okay. So the solution: M is 1 kg and R is 1 meter, and omega is 60 revolutions per minute. Again, to convert to radian per second, revolution, I told you, is one revolution is 2 pi radians. One revolution means a complete circle. That's 360 degrees. And 360 degrees means 2 pi radians. Because 180 degrees equal to pi radian. So 360 is 2 pi radian. That's why I have revolution equal to 2 pi. Then minute is 60 seconds. So, and you can convert that to get your answer. Okay? Then you have that already. First thing is to calculate the moment of inertia. And for a uniform circular disk whose axis of rotation is through the center, perpendicular to the plane, then our I is mr squared over 2, or half mr squared. M is 1 kg, I is 1 meter. So get your answer. You have half kilogram meter squared, 0.5 kilogram meter squared. And the second part, the energy stored in the disk. Energy stored in the disk. For energy, as a disk is rotating, it possesses kinetic energy. And for rotational bodies, kinetic energy is half I omega squared. Recall that, we did that. Okay, so substitute your I for 10, which is 0.5 kilogram meter squared, and your angular velocity, which is everything in bracket squared. Okay, everything in bracket squared. If you compute using your calculator, the value, energy stored in the disk will be 9.8696 joules. Energy is measured in joules. Okay, determined in joules. Another example: a bicycle wheel of radius 0.32 meter has a moment of inertia of 0.035 kilogram meter squared. The bicycle has a wheel R meters, correct? A moment of inertia in kilogram meter squared. And it is about its axis. Now, when the wheel is lifted from the ground and set spinning at a frequency, you now lift up that wheel and you set spinning. Maybe you use your hand, you apply a force. And the frequency, the spinning frequency is 10 Hz. It comes to rest after 3 minutes. So that means the initial, from this frequency, we are able to obtain the initial angular velocity and comes to rest final angular velocity, which will be 0 radian per second. 0 radian per second. Rest and final angular velocity. And the initial one is, the F is 10 Hz. And remember that omega can be obtained. Omega can also be obtained as 2 pi F. So 10 Hz, you can apply, you can obtain that. And the time it takes from the time you set it to motion and the time it comes to rest is 3 minutes. So what is the angular deceleration of the wheel? I told you earlier, when there is reduction in velocity, then there is deceleration. Increase in velocity means there is acceleration. That's it. So again, you also to determine what is the average, or to determine the average frictional torque acting on it, and the rate at which it dissipates energy as it rotates. Okay, so let's see how we do that. Look at that. That's the bicycle. Apply it, it rotates, and there you can solve. The solution: R is 0.32 meters, I is 0.035 kilogram meter squared, your F is 10 Hz, your T is 3 minutes, and convert that to seconds. That's 3 times 60 seconds. That's 180 seconds. You have your F, and from there you can obtain your initial angular velocity. I call it omega I or omega 1. And if you do that, you have 62 Hz is meters per second. 2 pi is radian, is in radian. Is that not? Anytime you see Hz, unit of frequency, Hz. Anytime you see Hz, it means per seconds. It's per seconds. And 2 pi, unit is radian. That's why you have is 2.8 radian per second. Then omega 2, final angular velocity, is 0, coming to rest. Okay, so what's the acceleration? You know this formula. You have t, you have omega 1, you have omega 2. So you know the right formula just come to mind. And that's your angular acceleration, alpha, equals omega 2 minus omega 1 divided by t. And you substitute omega 2 minus omega 1, 0 minus 2.8 radian per second over 180 seconds. And your answer will be minus 0.349 radian. So this, you are looking for acceleration. So a negative value shows you that it is not accelerating, it is decelerating. So deceleration now is 0.349. That minus sign shows that it is decelerating. Okay. Then B, the average frictional torque. And torque, there are several formulas to obtain torque, but in this case now the most relevant one is using the method of inertia and the angular acceleration, because we have method of inertia given to us. I have the angular acceleration, I and alpha. So you have your I, which is this value 0.035 kilogram meter square, and your alpha, which is 0.349 radian per second square. And you compute that, you have minus 0.012 Newton meter. Average frictional torque. Remember, the torque, that frictional torque will oppose the motion. Okay, so that what slows down, and that's mean already this side. It slows down friction in the torque as it's rotating. The frictional torque slows down the rotating wave until it comes to a stop. Then the rate of distribution of energy. Likewise, that illustrates that the energy is losing energy. That's the essence of those negative signs there. Okay, so rate of energy situation, that's power. Rate of energy, rate of work done, rate of energy expended, that's power. Okay, so power lost. Oh, and you know that formula also. That's why other formulas to obtain it for. In this case, now the relevant one is using our tau, the torque, and the angular velocity. Or the torque is obtained already, and the angular velocity is also known. Okay, it's also known. Even I can say the within that 3 minutes, the rate of energy distribution will be what? The torque, then omega 2 minus omega, okay, 1. And this case, because this one is 0, okay, also 0, omega 2 is 0, then we can, okay, omega 2 is 0, so we have our, omega 2 is 0, so we work with just omega. But if, let's assume the question is to determine the rate of energy distribution from when it was, the wheel was set spinning to maybe when the frequency reduces to 2x. Do you get it now? That means you have to also obtain another omega, another value of angular velocity when frequency is 2x. So in that case, you have to use the formula I wrote, omega 2 minus omega 1. Do you get it? If you don't understand it, you can listen to it again. Okay? So in this case now, tau is minus 0.012 Newton meter. That is the frictional torque, and the angular velocity is 62.8 Newton per second. If you do that, you have 0.75 watts. And that is the rate of energy dissipation. Negative shows that it is losing 0.5 joules of energy every second. That's what it means. It is losing 0.5 joules of energy every second. That's why it comes to stop. Okay? Then another example. The bicycle wheel of radius 0.3 meter can turn freely about a fixed axis. It rotates. Now, a steady force of 2 Newton is applied at a tangent. So that's the description. You see, F is applied at a tangent, and the application is for just 0.4 seconds. So the time of applying the force is 0.4 seconds, and the force applied is 2. Now, if the wheel starts from rest, the initial, it starts from rest as, I can call it again, omega I or omega 1. And the moment of inertia of the wheel is 0.5 kilogram meter squared. Find the angular velocity. Find omega F, which I can also call omega 2 after 0.4 seconds. So I am applying the force for 0.4 seconds, rotate it. So what will be the angular velocity after that? So we can obtain, very easy to solve. We know the torque, we know the force, we know the radius. So we can obtain the torque. Is that not? Yes. So let's see. Solution. What the parameters given is them out. Okay. We have to obtain the torque. Okay. And to obtain, okay, the first thing is, okay, I have to find angular velocity. And to find angular velocity, this is the formula. Omega F equals to omega I plus alpha t. We know the time, but we don't know alpha. We know this. So we have two unknowns, and so it cannot be solved, except it's an Laplace equation. It cannot be solved. So we have two unknowns, but what we have to actually obtain is this. The time is 0.4 seconds. So this is what is not known. We need to now obtain our alpha. And because we can obtain torque, and that's mean of inertia, which is 0.5 kilogram meter squared, and we can obtain torque, and because the wheel is perpendicular, F is perpendicular, the force is applied at the tangent to the wheel. So that means R and F are perpendicular to each other. And for them, we can obtain our torque, the RF, because the angle between them is 90 degrees. So sine 90 is 1, just RF. Okay? So if tau, the torque, is RF, so you can substitute RF equals to I alpha, and making your alpha subject to formula. You have RF over I. So you obtain your alpha from the angular acceleration, which will be 1.2 radian per second. And you substitute back into now the main expression, omega F, substitute F, which is equal to omega substitute I plus alpha t. So you have omega substitute I 0 plus alpha 1.2 radian per second squared, then times t 0.4 seconds, and your answer will be 0.48 radian per second. Straight away. Straight away. This is another example. We want to also look at it. Very similar to what we've been doing before now. We have R at rest. We have omega I as rest. And it rotates freely. When the force of 1.5 Newton, the force is applied. You see R and F2, they are perpendicular to each other, so 90 degrees between them. If its moment of inertia is this, I is given, determine its angular velocity, determine omega N. You have to determine it at t, when you have t. So you have your F, and you have your R. So this is not what I've done before. So we can go with this too and solve. Okay, and also do it more the same approach. You solve this expression, you obtain your alpha, and you also substitute your alpha back into the expression, and you obtain the final answer. Okay, jumps. This is another example. Moment of inertia. 80 kilogram meter squared. I. Rotating at 6,000 radian per second. Omega I. It was braked uniformly, consistently braked, and it stopped in 30 seconds. T. So stop 30 seconds means that it comes to rest. So that means your omega A substitute rather omega substitute is equal to 0. So this is your T. 30 seconds, that's your T. Now, what is the angular acceleration? Calculate alpha when the brake was applied. Then how many revolutions does it make during this time? How many displacement does it experience? Then what torque? What torque did the brake applied? What torque? Know that when you apply brake, there's a force. So what torque is it? Brake applied. So you can do it. Okay? You need to practice it. Write the answers in the comment section. Another example. We read the last example here. The turntable of a record player is a uniform disk of moment of inertia 1.2 times 10 to the minus 2 kilogram meter squared. You have I 1.2 times 10 to the minus 2 meter squared. Now, the motor is switched on. When the motor is switched on, it takes 2.5 seconds for the turntable to accelerate uniformly from rest. From rest means omega I is 0 and 3.5 to 3.5 radian per second means omega F. It takes 2.5 seconds time for the angular velocity to increase from 0 to 3.5 radian per second. So what was the angular acceleration? Okay, then B, what's the torque? What's the torque? Okay, what's the torque provided during this acceleration? What torque must the motor provide to cause this acceleration? What torque caused that acceleration? You see it? Very easy. And that's my case. I know you can do it. So provide the answers in the comments, and I believe you will do well in the exam. Please take time to study, go over the video as much as you can, understand, ask questions. If you don't understand any part of it, just comment, I will respond, and you will discover that these are very simple concepts. Okay, again, let's share this video with your colleagues, encourage them to study. Also, tell your friends outside the university about this channel, let them also benefit. I wish you resounding success in your academic pursuit. God bless you.